Okay, I think this is time to start. So welcome everybody again. Thank you for coming to this new Landscape Lab seminar online. So the presentation will be recorded and the record is already going on. So today we are pleased to welcome Charlotte Prud'homme from the University of Lausanne. We will talk about the long-term change in terrestrial environments and combining geochemistry and dating. So just a brief introduction. So Charlotte has made a study in France, in Grenoble, and just reminded me that I was a first-year bachelor teacher, so it doesn't make me more young. Then she moved to Paris for a PhD in geography, mainly with Pierre-Antoine at the LGP, and then moved to Germany at Mainz, the Max Planck Institute, for a few years. And then since last year, she moved to Lausanne to continue her research. So just to give you a brief, more details about the presentation and how it will work. So Charlotte will present her research for the next around 45 minutes. During this time, the chat will be closed. On a few minutes, or when we reach the conclusions, we will open the chat. So the audience will be able to type questions in the chat that we will ask directly to Charlotte. Or if you prefer, you can also raise your hand and we will reactivate your microphone so that you can ask directly your question. So that's all from my side. Yeah, just that I'm sharing, sorry, this Landscape Lab seminar with Michal and Dave, who are also here. You can see their camera on. And we will ask questions all together during the discussion. So if no more detail to show, I will give the stage to Charlotte. So please, Charlotte, the stage is yours.
Okay, so hi everyone. First of all, I would like to thank the Geomorphological group for inviting me to present my research in the Landscape Lab seminar. And I would also thank my co-authors because, of course, what I will show today is a teamwork with several collaboration. So as you know, landscape evolution responds to tectonics and climate. And today, my talk will focus more on the past climate perspective. The question that I would like to address is how can we link landscape evolution with past climate, and more precisely, how can we reconstruct long and short-term climate change in terrestrial environment? So I will present you an approach that I am developing, which combine geochemistry and dating of continental carbonate preserved in aeolian sequences. So the aim of my research is to better understand the past climate in terrestrial environment. What we know about climate dynamics is mostly coming from ocean and ice core with temperature proxy, as you can see here. There is a real lack of data on land, but we are living on land. So we need to better understand the past climate in terrestrial environment. So my research is focusing on the study of sedimentary archive at two complementary timescales. First, I will talk about millennial variability during the last glacial period, which is characterized by a global cooling and an unstable condition. But I will also talk about long-term Pliocene-Pleistocene transition, which is characterized by the onset of northern glaciation during Quaternary times. So my talk will be divided in two parts. During the first part, I will describe how periglacial environments are responding to short-term climate change by studying loess-palaeosol profiles. And then the second part of my talk will be focusing on the sedimentary sequence, which record long-term climate variability in arid environment. It's important to better understand this past environment as they are very vulnerable and sensitive to climate change. So We will first focus on the last glacial period. So the last glacial period is between two, it's located between two interglacial on the time scale. So this interglacial is today, and here is the warm phase is named aeolian. But we will focus on the last cold ice age, which a period which ranging from 110 to 12,000 years. And this period is characterized by the maximum extension of the ice sheets, which reached their maximum 20,000 years ago, so during the last glacial maximum. And this extension of the ice sheet is also correlated with lower sea level, which is about 120 meters below today, compared to today. And this, of course, these two parameters like change the landscape of north of Europe. But this period is not only characterized by a global cooling, but it's also characterized by an unstable climate, which is very well recorded in different archives. And the reference archive for this time is the Greenland. So here you have the delta weighting of the ice core, and you can, so we are here, I don't know if you see my mouse, but yes. So here we are here, and here is the aeolian, and the last cold ice age is here. And as you see, it's really characterized by an unstable climate. So we have the Greenland stadial, which are characterized by an abrupt cooling and more cold climate. And then you have the interstadial phase, which is defined by sudden warming over several decades, which are followed by gradual cooling over several centuries. And in Greenland, the difference, the amplitude between stadial and interstadial is about 10 degrees. We also have evidence for short-lived, particularly cold phases, which is derived from the coarse grain layer of the ice reef debris, which is preserved within the North Atlantic marine sediments, and they are known as enriched events. And these enriched events are associated with a significant drop in sea surface temperature and were coeval with the most prominent Greenland stadial. So we can see that this variability is well recorded in the Greenland, so in ice core, and also in marine core. But what is the impact of this short-term climate variability on terrestrial environment? So here is the last maximum permafrost. So the permafrost during the last glacial period was 33% larger than today. It seems reasonable to assume that this high mid-latitude experienced similar climate conditions during the Pleistocene that were similar to those of today. However, there is two major differences. One, the ice free zone area of the mid-latitude would have been in relatively close proximity to the continental ice sheets, which will lead to strong wind. So a little bit like the katabatic wind in Antarctica. And the evidence of this wind is the widespread occurrence of thick deposit of wind-blown dust, which is loess, and we can see and they are deposited in North America, in Europe, and also in Central Asia. The second difference will be because of the lower global sea level. Many areas of high and mid latitude would have been in more continental locations than they are today. So the Pleistocene periglacial environment would have been dominated not only by seasonal temperature regime as today, but also by a greater continentality, greater aridity, and great and intense wind. So which archive in terrestrial environment will be the best to see this climate variability on land? It's the loess-palaeosol sequences. So loess are, as I said, wind-blown dust, and they cover a large geographical area in Eurasia. They are deposited at the margin of continental ice sheets during the last glacial period. So the loess-palaeosol sequences are characterized by a rich and contrast record. So I study two sequences in the Rhine Valley, Nussloch and Remagen. So Nussloch is here, and Remagen, Schwalbenberg, is at 200 kilometers north. So Nussloch is a reference site for the MES2, so for this period, which because it's, as you can see, there is more than 12 meters of deposition. So it's a very dilated sequence, and it's record of a 17 meter from 55 to 20,000 years. And then I will talk about Remagen, which is a shorter sequence. It's but also in the Rhine Valley, about 5.5 meter, and it's characterized by a high resolution for the MES3. So the advantage of the loess profile is that their pedostratigraphy is characterized by an alternance between the accumulation of loess unit, which is here in yellow, which suggests cold and dry condition, and the formation of paleosoil or tundra clay, which indicating warmer and wetter condition. So tundra clay is this, and it's the active layer of a former permafrost. So it shows, by having this tundra clay horizon, it shows that we are in periglacial environment, and they were permafrost at one point in this sequence. So the active layer is just the layer which freeze and defreeze during seasonally. So the loess sequences are very sensitive to climate variability. However, they are very poor in proxy to quantify and reconstruct the past climate parameter. And my research addressed this problem. So I developed a new proxy, the Earthworm Calcite granule, which are preserved in loess-palaeosol sequences. So these granules are about sand, about the size of the sand size, and they are made of calcite crystal. They are formed by biomineralization processes in the calciferous glands of the earthworm, and then the earthworm are deposited the granule in surface and subsurface. So here is a log scale, so you can see that most of the granule are deposited in the surface. Moreover, we are working on fossil earthworm calcite granule, which were made during the last glacial period. So the earthworm was stuck in one layer because below it was permafrost, so it was frozen ground, so they couldn't go deeper. So they are stuck in this layer, and therefore there is less mixing between the layer. So how do we manage to extract this earthworm calcite granule from loess? So here is a sample strategy. So it's a photo for Remagen and here in Nussloch. So we took sample every 5 centimeters for 17 meter and 5 meter for Remagen, and we take 10 liters, so it's about 15 kilograms of loess, so it's a lot of sediment, because as I said, loess are quite poor, so we need a lot of volume to have a little bit of granules. And then we wet sieve them, so these big bags, either on the field directly or on the laboratory. And from these 15 kilograms, we then have, after wet sieving, we just have 250 grams. And then from that, we can hand pick the earthworm calcite granule under a microscope. So to test the reliability of this new proxy, I extracted and count granule along the entire sequence every 5 centimeters from Nussloch during my PhD. So this took a lot of time, and also in Remagen. So it's here in gray. So the granule counting, as you can see, is very well correlated with the pedostratigraphy. We have high concentration during the paleosol formation and very low concentration in loess unit. You can also see that the the granule counting is well correlated with the grain size and more particularly with the clay contents. So this show that demonstrate that the granule were formed during the formation of the horizon, of the Paleosol horizon. So this counting, this paleo-environmental approach, first of all, the first result was to show that the earthworm survived during the last glacial period. This was the first result. And then we can see that the earthworm has a very rapid response to environmental and climatic change. So earthworm calcite granule can be used as the environmental proxy, which is able to detect rapid climatic events. Another challenge in terrestrial environment is to provide a precise chronological framework. So we developed a new method. So for that, we date the earthworm calcite granule with radiocarbon. And you can see here still Nussler, and we did more than 40 dates for Nussler, and there is no inversion. I then developed an age model based on Bayesian statistic, and this model indicates a very high sedimentation rate, up to 2 to 1 millimeters by year, between 30 and 23,000 years. This validates the quality and the high resolution of the climatic record during this period. So we can now compare directly the loess-palaeosol succession of Nussler with the delta O18 here of the North Grips of Greenland. I did the same for the Remagen sequence, and we can see that these two sequences are complementary, as in Remagen, we obtain a very good record for the preceding period between 40 to 30,000 years, which are characterized by the development of well-developed Paleosol. So the radiocarbon dating on granule can be used to date and to identify climatic oscillation and confirm that the Paleosol are formed during Greenland interstadial, and then the loess unit are formed, was accumulated during the stadial phases. So now that we have a precise chronological framework, we can compare the loess profile between them, but also compare with the Greenland record or other record. So now that we have the time, it would be also interesting to quantify the past climate parameter, because this is the aim of this work. And the advantage to work with the granules is they are composed of calcium carbonates. So we can use their isotopic signature to quantify the land temperature and the soil moisture. And I will explain how. So first, we did so I select 20 sample of 20 layer of 5 centimeters for both the sequence. And I measure 30 granules by layer. So and I measure each granule individually. So here's the results for the delta O18 for Remagen and Nussler, and the delta C13 for Remagen and Nussler. So now how can we link the delta C13 of the granule to the soil moisture? So first, we need to know the source of carbon, and it's coming mainly from the diet. So we use the carbon isotopic fractionation, which were calculated between the carbon ingested by the worm and the carbon output in the granule, to be able to reconstruct the delta C13 of the plant. So we are around -24, so we are around here. We are in dry ecosystem, which is okay because we are in Paleosol formed during the last glacial period. So then we can use this equation where we need to know the delta C13 of the atmosphere, which is coming from the literature, so delta C13 of the plant, and then we can have the mean annual precipitation. Then from the oxygen composition, how can we have the temperature? So we know that the delta O18 of the granule is dependent on the temperature and the delta O18 of the meteoroid water. We use a calibration equation, which were made on modern earthworms. So they did like a calibration equation at 3 different temperatures. So we use this equation, but we have only one equation, and we want to know the temperature. We know the delta O18 of the granule, so we need to estimate the delta O18 of the meteoric water. To do this, we use a meteorological station spread over the North Hemisphere, and we use the equation between the air temperature and the delta O18 of meteoric water. And by combining these two equations, we could calculate the past temperature from the delta O18 of the granules. So here are the past land surface and precipitation. So you have the age, the insolation. Here is a record from Greenland with the delta O18 that we saw already. And here is the concentration of the calcium, which can be linked to a dust input in Greenland. So here is from the Rhine Valley, the sedimentation rate of both sequences. Here is the mean soil moisture. And here's the land surface temperature of the warmest months. Here we have the delta O18 of a cave in the Alps, and here's the ice, the Scandinavian ice sheets and British Island ice sheets volume. So what you can see, first of all, is the temperature are quite high because we have a mean temperature between 8 and 13 degrees. But what I forgot to say is like the earthworm are producing the granules when they are active. So during winter, during the last glacial period, during winter, the earthworm was not active, so they didn't produce any granules. So this temperature are summer or warmest months. So when the active layer of the permafrost was thawing. So that's why we have temperature between 8 and 13. So you can see in Remagen, we have very high resolution between 40 and 30,000 years. And you see that the stadial phase are cooler, about 1 or 2 degrees, than the interstadial phase. So this is good. But if you remember in Greenland, it was 10 degrees difference. So here on land is less, at least for the summer temperature. In Nussler, this part is less high resolution, but what is interesting is the higher part, so the MES2 from 30 to 20,000 years. In Nussler here, you can see the sedimentation rate is very well correlated with the dust input in the Greenland. And this dust input are also correlated with an aridification trend. So you can see here, which can be linked to this drier condition are recorded by the delta C13 of the granule. And so you have drier condition during the maximum extension of the ice sheet. However, we have wetter condition during the growth of the ice sheet. So the increasing of the precipitation may have contributed to accelerate the expansion of the European ice sheet. So this first part, so we demonstrate that the survival of the earthworm, the earthworm survived during the last glacial period. We provide a precise chronological framework which confirms that loess sequences are sensible to abrupt climate change. We provide as well the first millennial scale quantitative terrestrial climate reconstruction from northwestern Europe. We could reconstruct from the isotopic signature, the land surface temperature and precipitation. We also correlate, so there is a correlation between change in the ice sheet cover and extent of periglacial aeolian environment across the North Atlantic region during most of the last glacial period. And we saw that the terrestrial response to millennial scale climate oscillation was both rapid and synchronous, but not as extreme as in the polar or Mediterranean Sea region. So this was the first part of my talk, and now we will move on, and I would like to show you the second part where I will present longer time scale and how land scale responds to this long-term climate variability. So to compare, the last glacial is only here. So over the last 5 million years, the Earth have evolved from a largely ice-free world to a cooler planet, which are defined by 100,000 glacial interglacial cycle. So this transition is best understood via the marine perspective, as shown by the well-known stack of delta weighting of foraminifera, which show an increase of ice volume during the Pleistocene, together with an increase of amplitude of the glacial interglacial variability. So during this period, the first cooling event is recorded at 3.3 million years. However, the intensification of North Hemisphere glaciation took place a little bit later, around 2.6 to 2.7 million years. So this Plio-Pleistocene transition is important on the continent, especially in arid Central Asia, where the first loess accumulation is recorded at 2.6 million years and indicates the transition between a warm and wet environment to a more steppe environment. So one of the possible scenarios for establishing of this glaciation includes the change in ocean circulation, in particularly with the blocking of exchange of tropical water between the Pacific and the Isthmus between 4.6 to 2.8 million years. So this modification of the ocean dynamic brought two major changes. One, the establishment of the Gulf Stream in the North Atlantic, and a change in the salinity of the water of the Atlantic compared to the Pacific. So this might trigger the North Hemisphere glaciation. However, it is very unlikely that the continent play only a minor role in this evolution of the climate system. And this is the aim of our story. Understanding the contribution of land-ocean feedback is imperative in order to elucidate global climate feedback loops over the late Cenozoic. So one other hypothesis invoked moisture transported via westerlies onto the Eurasian continent, which will increase the outflow of the large Siberian rivers. And this injection of fresh water to the ocean is proposed to have expedited sea ice formation at high latitude. So here we interrogate the continental contribution to Northern Hemisphere climate feedbacks by reconstructing the last 5 million years of moisture variability in arid Central Asia. So our record derived from a 80-meter thick sedimentary succession in southeast Kazakhstan, so here, a region uniquely situated to investigate long-term land climate feedback. Its semi-arid climate is derived by the interplay between the mid-latitude westerlies, the high-latitude polar front, and the Asian monsoon. It's also characterized by very high mountain range, which play a critical role in influencing the dynamics of this climate subsystem. So the Neogene uplift of the Himalaya and the Tian Shan mountain range to the south and the retreat of the Parathetis Sea on westward mitigates the penetration of the monsoon precipitation to arid Central Asia since the Miocene and drove long-term aridification. We have to know that the arid Central Asia most continuous archive accumulate along the Piedmont. So aeolian sediments were transported by air masses associated with this major climate subsystem. So our focus here is Sharin Canyon section, and we undertook stratigraphical description and sampling of this 80-meter thick sedimentary succession vertically by abseil to ensure continuity. So we construct this composite stratigraphy at Sharin Canyon. So on the stratigraphy, we have a silty matrix through the entire sequence with different processes of carbonatation. Here we have the low field magnetic susceptibility, which is lithological driven with sharp increase, which correlate with a mafic gravel layer. So we have different environments. We describe 3 different environments in this composite stratigraphy. So the lower stratigraphy unit is imbricated gravel and silt, which indicate a low gradient, poorly constrained channel flow, and it's indicative of very high energy transport. This is overlain by 24 meters of alternating aeolian loess and subangular non-imbricated alluvial fan sediments. And the facies association indicate a mix between alluvial and aeolian system, where short-lived and high-energy wet episodes punctuate an overall background aeolian deposition in semi-arid environment. And then the entirely aeolian deposit of the uppermost 43 meters document a more arid regime and are characterized by massive, well-sorted loess and intercalate precipitation of pedogenic carbonate. So the overall transition from a waterline sediment to a mixed alluvial aeolian deposit to pure aeolian accumulation suggests a sequence of aridification which responded to climate variability. So as I said, the challenge is always to give an age and to provide a chronological framework. So here, the chronology of the Sharin Canyon sequence was determined by using paleomagnetism, which is a relative method. And we also use uranium lead dating on carbonate, which is an absolute method. So it gives us some point to be able to build our edge model. And our edge model indicates that the entire sequence accumulates quasi-continuously over 4.5 million years, from 5 to 0.5. So providing one of the largest known continental record on environmental change. So the water lane here is are deposited between 5 to 4 million years. Then the mixed alluvial aeolian between 4 to 2.7 million years. And then we have the aeolian deposit from 2.7 to 0.5. So we reconstruct long-term moisture variability using the delta C13 of pedogenic carbonate as a proxy of aridity due to its sensitivity to soil respiration. And we also use the delta 18 of the pedogenic carbonate, which vary as a function of both soil temperature and delta 18 of the meteoric water. We quantify change in soil temperature using clumped isotope analysis for 3 key time slices representing minimum, maximum, and mean delta 18 of pedogenic carbonate values. So as you can see here, even if the stratigraphy is showing an aridification, the aridification is not linear. And we have, so here is the delta C13, and we have a correlation between the sedimentation rate and the delta C13 of the pedogenic carbonate. So we start the sequence with quite stable condition, which is associated with a constant sedimentation rate. And then we have the first drying phase from 3 to 2 million years. And this is also evidenced by increased sedimentation rate and an increase of delta C13, which oversaw the establishment of a purely aeolian deposited regime from 2.7. Then we have a period of increasing precipitation and decreased aeolian sediment flux between 2 to 1.5. And then again, we have an arid condition which intensify from 1.5 to 0.5. We can see here. Our delta 18 results indicate variability in both temperature and moisture source through time. And you can see that the delta 18 are reproducing the trend of the delta C13 with stable condition increasing, so cooling cooling phase, a warm phase, and then a cooling phase. So we use the CLEMT isotope to quantify the temperature. So we have a temperature between 8 to 13 degrees, which this Pliocene, early Pleistocene temperature fall within the range typically of more than near surface temperature for this region. So based on the stable isotope record of pedogenic carbonate, we suggest that the Sharin Canyon sequences record Plio-Pleistocene variability in moisture and sediment transport over arid Central Asia, which is modulated by the interplay between the westerlies, which bring the moisture, and the northerly air masses, which are associated with the Siberian high pressure system, which is a semi-permanent anticyclone, which is centered over Eurasia in winter. So now we will try to reconstruct the paleoclimate at these 4 different time scales and see how these 2 climate masses was interacted. So in the early Pliocene, we have relatively warm and wet conditions. The rainfall is likely derived from westerlies, air masses, which is boosted by the North Atlantic current following the 4.6 million years, the shallowing of the Panama Seaway. And the landscape in arid Central Asia, responding to this atmosphere-oceans feedback through enhance of the fluvial activity at Sharin Canyon and by extension in Siberia. So the inflow of the fresh water from the Siberian River to the Arctic Ocean enhance polar sea ice formation by reducing salinity, which creating a terrestrial tipping point for the largest cooling event of the Pliocene. Then, during the Plio-Pleistocene transition, we have a cool and arid condition at Sharin Canyon, which persist until around 2 million years. So this cold and dry climate were also recorded further north at Lake Baikal and in Arctic Siberia. So the cooling and the global aridification reflects intensification of the Siberian high, which brought cooler temperature and blocked the westerlies moisture transport over Eurasia. So the weakening of the westerlies airflow could be linked to the North Hemisphere glaciation. And once established, this glaciation oversaw a decrease in sea surface temperature in the North Atlantic, which further reduced the evaporation and weakened the moisture transport onto continental Eurasia. So here we have an increase of the Siberian high and a decrease of the westerlies. Then we have this phase. So the early Pleistocene, it oversaw an abrupt reversal into warmer and wetter condition in arid Central Asia. So we have a coeval reduction in polar jet activity over Eurasia, which resulted in the particularly warm interglacial temperature, which is observed in the Arctic. So this, along with stronger westerlies associated with the increase of evaporation over North Atlantic water, will likely have weakened the Siberian high, which promote water condition and increase precipitation at Sharin Canyon as westerlies derived rainfall penetrate further east. So here we really have an increase of the westerlies, which will bring moisture, and a decrease of the Siberian high. And then so the aridification in Central Asia, it's intensified at 1.5 million years, and this drying trend persisted through the mid-Pleistocene transition, which is associated with rapid cooling of sea surface temperature. So the increase of continental ice volume lead to an intensification of the Siberian high and to a decrease of evaporation potential of westerlies, which originated from over the North Atlantic. So we have a weakening of the westerly moisture flux and a stronger polar jet, which is associated with the Siberian high increase, which drove the aridification across Eurasia. So landscape in Chine Canyon evolved from fluvial to aeolian environment, and this is related to climate. The Chine Canyon sequence provides the first opportunity to interrogate the long-term terrestrial interaction between mid-latitude westerlies and high-latitude climate system, and the response of Earth surface dynamics to Plio-Pleistocene climatic change in Central Asia likely generate terrestrial feedback, which affect atmospheric and ocean circulation, leading to tipping points in the regulation of moisture transport and sediment flux. So I developed a new proxy, which was associated with a precise chronology framework. This will help us to better understand the climate dynamics in the terrestrial environment. And the quantification of land surface temperature and soil moisture is important. And I'm hoping to develop this approach to other sequences to build a database in terrestrial environments. And on longer time scale, stable isotope of pedogenic carbonate is very useful to characterize the past climate and could help us to better understand the interaction between ice, ocean, and land. Thank you very much for your attention.
Okay, thanks a lot, Charlotte, for this really nice talk on a nice tour of different locations. So as Aditi has written in the chat is open now for questions. So if anybody of the audience has questions for Charlotte, please just write your message in the chat and we will repeat it to Charlotte, or you can also alternatively raise your hand. There's a button somewhere in Zoom. You can raise your hand and we will activate your microphone for you to ask directly your question. So if waiting that some people are typing the question, I have one question for this, the last part of the presentation that you've shown us. Mm-hmm. For the very recent part, for after 1.5 million years, we see an aridification and a change in the delta C13 and delta 18, but not really in the sedimentation rates. They do not increase really. They stay very, very low compared to the last period where we saw this aridification, but also a kind of a jump in the sedimentation rates. Is it something that you have looked for, or can it indicate something like a change in the the provenance of the material?
Yeah, so thanks. It's a very good question. So first of all, so this, I don't know if you saw, but I keep this color for the 3 different environments that we described from the stratigraphy. So we are in the aeolian deposit. So it's true that we should have had a stronger and higher sedimentation rate, but we also but we have high sedimentation rate for this period, and then we have this warm and wet condition, and then it's going up again for aridification. So why we don't have an increase here? So we have a little bit of increase at 0.6, but it might be because of provenance. So it might come from the sediment might come from somewhere else, but still we see like we are still in aeolian sediment. So on the stratigraphy, it's really loose. It's very dusty with carbonate, with more carbonate. So so it might come from a difference of provenance, as you said, as you suggest. Yeah.
Okay, thanks. I think we start to have some questions. I will let Aditi and Miral starting.
All right, I'll start then. Our first question is from Toby Hasse, and he's asking, well, he thanks you for the wonderful talk, and he's asking about the Caspian and Aral Seas near Kazakhstan site. Do you see corroborating evidence for the moisture regimes that you see in the last sequence?
Yeah, so thanks for the question. So the thing is, it's from terrestrial environment. These 5 million years, I couldn't 5 million years moisture record. I could really compare with other record because there is no existed. So, but I can compare different section of my stratigraphy. So yes, we see some evidence with the Caspian and Aral Sea. But what I would like to do now is to go a bit further north to see if what I record with the Siberian High, if I can go a bit more north to really compare with what I see on Charing. But yes, we can have this, we can collab. I mean, there is a correlation with recording the more east.
Okay, thanks for a great talk, Charlotte. There's a question by Trevor, and he asked that so he says 2 fantastic studies. A recent paper correlates Lake Sugetsu in Japan with Greenland post the LGM. Have you compared your first study results with that result?
Okay, thanks for the question. So no, I didn't, just because I'm a bit older. So my loess sequence from the first part of the talk stop at 20,000 years. So this paper that you talk about is after the LGM. So it's true that I didn't compare with my record, but yeah.
Okay. Is there any other question? Miral, Aditi, would you have one? Yeah.
Yeah, I have a quick question. So you talked about ECGs, and I mean, that's a great proxy that you're looking at. Is there a specific species of earthworms? I think I saw a name that produces these ECGs, or like all earthworms, or?
Yeah, so not all earthworms are producing the granules. So I had to dig a little bit in earthworm ecology during my PhD. Still doing my postdoc studies. So there is the Lombriscus terrestris are the most important, like as a species, is a species which is producing the more granules, but it's really huge compared to other species. Like for example, another species will produce 1 granule, whereas the Lombriscus terrestris will produce 100 of granule for, I don't know, like on a month or something like that. So we assume, and also Lombriscus terrestris produce the larger one. So I didn't say on the talk, but I focus on the granules which are larger than 0.8 millimeters. So we assume that these granules were produced by Lombriscus terrestris because they are present right now in Eurasia. We have it in Germany and in France as well, because I also work on French sites, and yeah, we can have these granules. So it's mostly from Lombriscus terrestris.
Okay, thanks.
Okay, there's one question in the chat by Gabor saying great talk, congratulations. On having several questions, but one particularly, so the soil carbonate clump isotope temperatures, which are quite low, are they representative of which seasonal temperatures? And to elaborate on this, in semi-arid areas, this tends to be the summer season, which my own data confirms based on analysis of soil carbonates formed over the last interglacial in loess-palaeosol sequence, so in Hungary.
Yeah, thanks, Gabor, for the question. So yes, the clump isotope of soil carbonates are seasonally driven, and it might be summer temperature, but it's true that it's quite low. But after I took really the extreme, so my lowest delta 18 and my highest delta 18, so value of pedogenic carbonate. So it would be interesting to do more. This was just to give us a range of temperature. So it's quite low for for summer, but in the same time, actual temperature there, it's for the mean annual temperature, at least it's the same range. So we need to dig a little bit into that and do maybe more than 3 clamp isotopes. But this was really to try to do clamp isotope on this pedogenic carbonate.
Okay, so we have one more question in the chat from Bernard, and he's asking, what information do you have about the active layer thickness in your sections? What is the influence of temperature on the activity of earthworms in paraglacial environments, I guess, or environs?
Okay. So if I go back here, yeah. I don't know what information. So about the active layer thickness, so it's characterized in Paleosol, in loess-palaeosol sequence by the thickness of the tundra glacier. So we have here in gray, so we have this tundra glacier formation, which is the active layer of former permafrost. So we assume that the active layer was this thickness, and then below it was permafrost soil. And then, so what's the influence of temperature on the activity of earthworm? So if I can go here. So we represent, so the granule, so the earthworm are producing the granule when they are active. So this is a bit linked to the question of Gabor, which it's seasonal. So we are recording the summer temperature. So when the earthworm are active and producing the granule. So we have the tundra glacier are mostly formed during the upper part of the sequence, so during the MES2, and we have a difference of temperature between MES2 and MES3. So it was cooler during the formation of tundra glacier than the formation of the paleo soil, of the Arctic brown soil, for example. So yes, we could record the degrees of temperature thanks to the granule in the active layer of the former permafrost in the periglacial environment.
Okay, so we have another question by Toby. He said, thank you for the answer about the seas to the east. Is the margin of the Siberian high and the cold fronts in Central Asia and the sensitivity of the system partly due to the drainage basin arrangement? I'm thinking that a small shift could deliver large amounts of water to north-flowing rivers versus internally drained basins or southeast flowing rivers in Central Asia. Am I wondering about other places to observe variability in the system?
Okay, thanks for the question. So if I go back to here, I guess, or here, maybe here. So the Siberian, because I can't, yeah, okay. So the Siberian high here, no, here we don't see. Yeah, it's an interesting question, and yeah, so it might be due to drain basin, but so the increase of the if I come here, the increase of the river flux, the river discharge in the Siberian the Siberian river, which friction with had an input of fresh water in the Arctic Ocean, but so this was linked to actually not the Siberian high, because we had the Siberian high will block the temperature. I mean, will block it's an anticyclone, so we don't have any precipitation. It's very arid and it's very cold because it's mostly done in winter. So this river discharge is really linked to the westerlies. which is input from the change in the North Atlantic current. That's why I would like to go into more to go in more detail in Siberian region, because we really are here at the interface between the westerlies and the Siberian high, but we are at the limit of the Siberian high. So I would like to go, if I can find a loess sequence very like near like Baikal or something like that, to really see if how strong is the Siberian high in this region. I don't know if I answer the question, but
okay, let's see if Toby can ask again if he has another question.
Okay.
Apparently he's happy about the answer, saying thank you. There's another question by Eitan saying thank you for an excellent talk. Following Bernard's question, did you notice a correlation between paleo temperatures and the thickness of the active layer as preserved by the paleosols?
Okay, so here we go back to the first part of the talk. Okay, maybe this paleo temperature. So alors, this is a little bit complicated question, because why? Because we are in terrestrial environment, so we have some erosion and some accumulation, and this is due to local topography or to local processes. So, for example, so some tundra clay, I know it's, I mean, they are well preserved in several profiles, because this I show one profile of Nussler, but actually there is several. So some active layer, we can really, some tundra clay, we can really see the same thickness. But for example, this tiny tundra clay, it has been eroded, and on the other sequence, it has a higher thickness. So, but this was the profile of my PhD, so that's why I did some analysis there. And then, so I didn't notice a correlation between the temperature and the active layer thickness. But what I can see, as I said, is like we have higher temperature during paleosoil formation than during tundra clay. But linked with the thickness, I can't tell.
Okay, apparently the answer is also satisfying. I just have one question for this slide, if I can. For the Remagen section at the bottom, you have this correlation between the clay and the ECG, but there's a slight offset. I mean, between the two. I mean, there seems to be a late peak in the ECGs compared to the clay. Is it something related to paleogenesis, or I have no clue?
Yeah, so so the thing is, in Nussler, you can see that before we thought like, okay, when there is a paleosoil formed, there is no dust input, and then when we have the loess, there is again a loess accumulation. With the granule, we can see that this is not true, because normally, as I said, the earthworm are producing, if I go back, the earthworm are producing the granule at the top soil. So then we should have a profile like that of the granule, like very high at the top and lower at the bottom. And if you see in Nussler, the peaks is at the middle of the soil. It means that there is always a little bit of accumulation of sediment. But here in Remagen, we are the top of we have higher, the higher concentration is linked to the top of the paleosoil. So we have a little difference between with the clay, but we have the top of the highest concentration of the granule are linked to the top of the paleosoil. So it might mean that the sedimentation rate was lower than in Nussler and maybe stopped during the paleosoil formation. And this paleosoil are much more developed than in Nussler. So they are in the same area in the Rhine Valley, but they are not exposed the same. So it might be, this might be, again, a local fact that here the sedimentation rate is lower almost stop during the Paleosol than here, and this can be shown by the granule. And the link with the clay, yeah, it's like 2-3 centimeters below, so it's less well correlated than in loess-palaeosol, but it's still, we still have a correlation.
Okay, thanks. Is there any other question in the audience or within the chairpersons? And I don't see anything. If you have a last question, please do write in the chat or do raise your hand.
I can ask a quick question while people are still thinking of writing something. You spoke about the earthworms being active and producing granules at a certain time and then not producing it. Is that because of response to climate, or is because they don't survive? Like there's only one season in which they're living or something, or?
No, so one part, so yeah, thanks for the question. So one thing was so earthworms are living in our temperate climate, right? And there is some species we can live in permafrost environments. So there is some species which can live in Russia. But of course, these species are not producing granules. So that was a big interrogation point during my PhD, is how can we have this granule produced by earthworm, which should not live in permafrost environment? Because today, if you put a terrestrial, Lombriscus terrestris in the permafrost, it won't survive. So how do they survive? So first, they produce the granule when they are active. So this is for sure when the active layer is thawing. So then they are active and they can produce the granule. So that's why we are recording only one season. But how they survive is, so they don't die. They try to, there is a lot of, I think that, okay, there is most of them should die, but but then they don't die, all of them, of course, and they try to overwintering. So the earthworm are overwintering, and they put in like diapos, so it's like they are not active, they just try to survive. And then how they survive, it's with the cocoon, which is like an envelope which protects the egg. And this can survive, they are cryo-resistant, and they can survive to very cold temperature. There are like some experiments on modern eggs of earthworm, which can survive at in the soil below 0. So they don't produce granule when it's very cold, but they survive, and then they produce granule when the conditions are better for them.
Okay.
Great, thanks.
Okay, I think there's no more question in the chat.
There is one, but directly to me from Bernard, so I can just say, might you know whether the classic loess sequence in China contains warm granules? If not, why not? So yes, I tried to look on Chinese loess to have some granules, but there is no granules. I didn't find any. Why? Because I think it's too arid. So they can survive in cold environment, but not in arid environments. So yeah, so I tried, but no, there is no, I didn't find any granules.
Okay, great. I think it's 5:05, so it will be time to close this discussion, except if anybody has a final question. If not, I will thank you again, Charlotte, for this very interesting talk. Thanks everybody for attending and for the discussion. And please come back next week. We have a next talk about glaciers by Anne Rowan on the same date, like Thursday, same hour. Thanks everybody, and have a nice day or a nice evening.
Thank you. Bye.